All right, welcome everybody. Thanks so much for joining Dana Vasali, our naturalist here in the Methow Valley. For how many years have you been doing your magazine, Dana?
This is year 29. I guess the spring will be the start of the 29th year. A long time. Methow Naturalist, yeah.
Fantastic. Yeah, so here we
It's an
go.
interesting
We're going to
it's
learn
an
about
interesting
the fauna.
process. Yeah. It's an interesting process because I think, oh my gosh, I have to do another issue. And then when I get it started, the enthusiasm starts to rise because the planet is so interesting. and and you burrow into these subjects and you just feel the excitement of being alive on the planet. So I'm fortunate because I couldn't do it if the enthusiasm didn't reappear every time. And hopefully that'll be the case for the slideshow too. So thanks to everybody for joining in. And this is more or less on fauna of the Methow. The fauna of the Methow is not so different than the fauna of the planet. It's an evolutionary story. And I have long thought of the Methow as kind of a laboratory for the planet, being as this is where I am. We have a microcosm of the whole journey on the planet. And the planet is on a journey. That's, in a way, one of the more interesting aspects to me. It's part of the big history story that that is being uncovered by humans, that life is on a journey. Life didn't even exist once on the planet, and then all organisms are related. There's biochemical evidence that all organisms are related to all other organisms. So that's work with here in Methow Valley. So I'm not sure where I got this picture. I certainly didn't take it. It's possible I meant to check with Ken Bevis and see if he got it from a trail camera. In any case, I'm not sure where I got it, but it's a great shot. And it illustrates a couple things. It illustrates the fact that life is not so easy. Life is a struggle for energy, especially in winter. Life is a struggle for energy. This is a golden eagle and a coyote on a dead mule deer. I would say the mule deer was almost certainly hit by a car, and the road's not very far away. And they're fighting over the energy that's embodied in the meat in that deer. The, there's no photosynthesis. I see off to the left there. There's a bitter brush. The leaves have fallen off. No photosynthesis. The sun has gone to the southern hemisphere. And so it's an energy bottleneck. It's often described that way. In biological terms, there's barely enough energy to get through the winter unless you can shop at Hank's Market. That's our market here in the get food, which is quite remarkable. Most of it is, I would say all of it is transported here by diesel trucks from far away. We live in an energy bottleneck, but there's another aspect to this there's another aspect there's this competition for survival that is built into the system. There's also all this beauty.
Here you are.
Golden eagle's beautiful. The deer is beautiful, even though it's dead. And that's the nature of life. The paradox of beauty in pathos, I would say. So a quick review. We talked about geology on the first program 2 weeks ago. And this is a mid-oceanic, it's an image of a mid-oceanic ridge and molten rock rising from the mantle and cooling as it hits the ocean floor and being pushed apart to in this case, well, I'd say east and west towards the continents by the molten rock that is continually pouring out of these mid-oceanic ridges. So that's a big story in its own right. Why is it so hot? I think, let's see, the mantle is about 7,000 degrees. The core is 10,000 degrees. The surface of the sun is 10,000 degrees. Why is the center of the Earth the same temperature as the center of the sun? I have a couple of interesting quotes by a biologist who was active in the early 1900s. JBS Haldane. JBS Haldane. He's famous for a humorous statement saying he was asked by a priest what he'd learned about God in his study of insects. And Haldane answered, God has an inordinate fondness for beetles because there are 400,000 species of beetles on the planet. So apparently God likes beetles. That's a lot of beetles. But he also noted, he said, the universe is not only stranger than we think, it's stranger than we can think. There is an enormous element of mystery wrapped up in the evolutionary story of the universe and of life on Earth. And just the fact that the Earth itself is so dynamic, I think, points to that mystery. How is it possible we can live on this planet where the mantle is 4,000 degrees and it's not that far down? I showed this slide last week. It's a nice diagram of how plate tectonics work. On the right would be continental rock. On the left is a mobile rock called a terrain that is embedded on the ocean crust. It's moving with the ocean crust, but it's not the same kind of rock. It's somewhat lighter, has more silica in it than the ocean crust. So when it is pushed against the continent, it's scraped off. And I showed a slide in the geology section. Most of the Pacific Northwest is made up of terrains that were carried onto the continent by the motion of plate tectonics. So before it hits the continent, before the terrain is pushed onto the continent, there's sediment running off the terrain and off the continent into a shallow sea. And then it's crushed by that terrain that's moving in to the continent. And that is a brief story of the Methow Valley. Much of the Methow Valley is made up of sediments that were laid down in an ocean. They were obviously laid down horizontal, and now they're almost vertical. And here's a picture of Twist Formation ocean sediments. This is right near the Winter Post Office. It's at the top of the hill after you leave going towards Twist. Unfortunately, you can't stop there because everybody goes 65 miles an hour. But that's what we have all around us is this history of the evolution of the planet. And there are a few marine fossils in the Twist Formation. This might be a little small for seeing, but I circled a couple things. This is a stratigraphy of the Methow Valley, and I can email this to anybody who wants it. Just send me an email and ask for it, and I'll send it to you. But the Twist Formation is down there at the bottom. It's 200 million years old. That's what we just saw. That rock at the Winter Post Office was laid down 200 million years ago. The youngest formation is at the top, Pipestone. Anybody who those of us who live here in the Methow, we all know about Pipestone Canyon. It's not young. It's 65 million years old. People have gone there looking for evidence of the asteroid strike, which happened 65 million years ago and failed to find it. But there are terrestrial fossils in Pipestone. It's not a ocean sediment, it's terrestrial sediment. And then these other formations. In the middle, just above the middle, is the Winthrop Sandstone. That's 135 million years old. They found 135 semi-tropical plant fossils in the Winthrop Sandstone. So this next picture is just a easier. Oh yeah, there are these unconformities. I wrote these numbers in here. This is Julian Barksdale's stratigraphy. He put this together. Julian Barksdale has been dead for a while, but he was the Methow geologist for 40 years and did most of the geology in the valley. But he didn't put in how many years were missing. He put in that wiggly line that's under the words I just circled in red. And this wiggly line indicates an unconformity. There's rocks missing. In that particular one, it says 6 million years have been eroded away. And that's the way it goes. I think there's one here. I can't read it very well, and you probably can't either. It's 50 million years of rocks are missing. They were laid down. There was a period of erosion that they can tell those rocks are gone. They went into the ocean as sediment, and then new sediment began being laid down. So it's a big story, a long story. So this is just an easier view of the same thing, a more artistic version of the stratigraphy of the Methow Valley, it doesn't have as many formations, but they're easy to see. Some of them, there's the one I mentioned, the Winthrop Sandstone. So there's another interesting point here. Over on the right, it says paleocurrent. And I think it sort of always strikes me as a surprise, a little bit non-intuitive. The sediments come from both directions. The continent was to the east. The North American continent that was slowly being built by these terrains being carried in was to the east. They said so the sediments are going to be coming off the continent from the east, but the terrains that are moving in on the ocean crust, the moving ocean crust, are to the west, and they also create sediment. And the geologists are so insightful that they can tell what direction the sediments of these various formations came from. I might have showed this last week. We talked about plants last week. Hopefully you can read that. The big portion of the plants there are dicots. We talked briefly about monocots and dicots. Some of you know what those are. Those are both flowering plants, two very different evolutionary groups of flowering plants. In fact, it would seem they're so different that I think flowers evolved twice back more than 100 million years ago on these two different lineages. And but they make up the bulk now of the plants on the planet in terms of species diversity, not in terms of biomass. Because if you were to weigh the gymnosperms, which are the conifers, they would probably weigh more than the flowering plants. They cover the northern and southern extremes of the continents, like the boreal forest in Canada. So these are the plant. This is the evolutionary picture of the plants on the planet. Down lower, it says bryophytes. Those are mosses. There's 16,000 species of mosses on the planet. This is out of E.O. Wilson's book, The Diversity of Life, which is 20 years old. And these numbers would have changed a bit. I know that they now say that there's 300,000 species of flowering plants. If you add up those dicots and monocots, it doesn't come to 300,000. It just, things change over time. But this is a basic picture of plant life on the planet. Flowering plants dominate in terms of diversification. It's very successful. So we're talking about animals this time around. So here's a similar diagram of the diversity and abundance of the animal kingdom. So there in the lower left are the beetles. Coleoptera, that's why Haldane said God has an inordinate fondness for beetles. There's more beetles than anything else. And that number is now 400,000. It says 290,000 there. That's because Wilson's book, The Diversity of Life, is probably 20 years old. So this is a picture of life on the planet. Most of these organisms are in the Methow, which just is to say the Methow is a window into the evolution of life on the planet. Those of us who live here can study life in the Methow and get a good picture of what's occurred on the whole planet. A few other things here. Chordates are here, creatures with a backbone. Down here is Platyhelminthes. That's I point that out because I'm about to pull up a picture of a flatworm. Oh, periphery, I forgot. There's a flatworm. So I took that picture through my microscope. That's just some sludge off a rock in the Methow River, and there was a flatworm swimming around. It's really quite interesting to see. These actually, these spicules here are silica diatoms, probably made out of glass. Not super clear in that picture. But the point is, we have these, or most of these organisms exist in the Methow. The evolutionary journey of life. We talked about this last week. We don't need to dwell on it too much, but there is a major split in the evolution of life, and that is the prokaryotes, which has that word down there in the bottom left, and the eukaryotes in the upper right. They're different types of cells. The prokaryotes are really characterized bacteria. They're vastly smaller cells than the cells that make up our bodies, which are eukaryotic cells. They're vastly simpler. They have no nucleus. They're 1/100th the size, but they are alive. And somehow they have the necessary complexity to be alive. So life has been divided into these three domains: bacteria. The word "eu" says eubacteria, EU. Eu just means true. True bacteria. The archaea, which are different enough from bacteria that they get their own domain. Um, to our eyes, they're similar to bacteria. One thing, they're invisible. They have no nucleus like bacteria. There are interesting aspects about them that we probably shouldn't go into, and not that I'm so knowledgeable about archaea. They're just tougher. They live in thermal vents. They live in the hot pools of Yellowstone. They can take far more radiation. You can shoot them out into space, and they survive the radiation. They're organisms that could live in the environment of the early Earth before the radiation coming from space was blocked by the oxygen that life put into the atmosphere. So life has differentiated. This is a simple version. I'm going to skip that. It's a big deal. That was endosymbiosis, one cell eating another cell, but the two cells then starting to live together instead of digesting it. And that I'm not skipping it, but eukaryotes, our cells, have organelles inside, and often those organelles appear to have formerly been living organisms that then began to live inside the cell. Bacteria do not have organelles. This is another picture of the diversification of life. I have those two words, prokaryotes circled, eukaryotes up at the top. So bacteria and archaea are down lower. They did appear earlier in the evolution of life. This is somewhat outdated to try. I've tried to understand the updating of the evolutionary tree of life, and it's grown quite a bit more complicated. And I don't think it's widely agreed upon. Uh, it's very difficult to understand. So this is a picture we can understand. I think it's adequately functional for our needs. We know that plants are different than animals and fungi. Algae are arguably single-celled organisms. The protists over on the right. I mean, there are algae that, in the ocean that don't look single-celled, but they are communities of cells that don't function as a single organism in the way that our cells do. So the point is life has diversified over time. And I pointed that red arrow down at the bottom because it seems that life only appeared once on the planet. They call it the last universal common ancestor, Luca. Everything is related. And that relationship is traced by biochemical similarities in all cells. I think I showed this last week. This is the plant kingdom. And the point here is there's an evolutionary trend towards greater complexity and larger size. That might be, some people might argue that, but obviously plants have gotten much bigger. Redwood trees are rather bigger than mosses and hornworts. And there's this complexification in their organization, this increase in the number of X's, which are labeled at the top. Early plants don't have a vascular system. Early plants didn't create seeds. Early plants didn't create wood. Early plants didn't flower. Early plants couldn't retain moisture, so they couldn't colonize the dry land. They had to live either in water or at the edge of water. So life is on a journey, and it's not finished. That is the most fascinating thing to me, is that life's on a journey. I mean, the most touching aspect of that is, and this is not part of this program, it's just meaningful to me, is the evolution of intelligence, the ability to understand our world. That is an emergent property of Homo sapiens, and it's obviously not fully developed yet. So I circled the number of species in the Methow just to show that the Methow is an evolutionary laboratory for life on the planet. Almost all the organisms that we would list in the plant kingdom are here in the Methow. Nobody's found any hornworts. There's a question mark on the first one, stoneworts, just because we don't know how many. We do have stoneworts. I talked about them in the plant section. But the other ones are big enough to see, and we can count them. There's only one cycad. It says there's only one cycad in the Methow, and it's in my window. I ordered it. It's a potted plant in my house.
You gotta give it a second.
This is a similar graph of animals. It's actually the order slightly reversed. Instead of the actual organisms being on the vertical axis or on the horizontal axis, but the effect is the same. I'm going to put in this red line to show that there's something going on. There is an evolutionary trend in the evolution of animals over time. There is an increase in complexification, and a lot of it, like with plants, is an increasing ability to colonize dry land. Fish don't have to worry about colonizing dry land. Amphibians means two lives. The word amphibian means two lives. The amphibians live the first half of their life in water. They actually metamorphose into a completely different creature. They have gills in their larval form and lungs in their adult form. Amphibian means two lives. So they hop out of the water. The frogs live at the edge of the water, but mostly they can't leave the water very far. There are a few amphibians that can live independent of water. Reptiles, they live shelled egg. They don't need to lay their eggs in water. Same with birds. Mammals give live birth. The evolutionary trend is a greater capacity to live on land. That's a picture of the sun. The sun is our energy source. We don't think of it too often. We might think of it today. It's just coming up. Yeah, it's up. It's 93 million miles away. It burns 600 million tons of hydrogen a second. And it's been doing that for 4.5 billion years. So, like that quote by Haldane, the universe is not only stranger than we think, it's stranger than we can think. I mean, I don't think there's any way to grasp the dynamics of star, much less the stars of the Milky Way, much less the now uncountable number of galaxies. It's just phenomenal. So, briefly, the sun is fusing hydrogen into helium. There's a slight loss of mass, which is released as energy. I don't know how Einstein, well, I do know how Einstein figured it out because the next slide shows you how Einstein figured out E equals mc squared. C squared is the speed of light, 186,000 miles per second squared, which is 670 million miles per second. And that's what you multiply mass by to figure out how much energy you're going to get out of mass. So here's how Einstein figured it out. He did it experimentally. This is a cartoon, I'll tell you. It's not for real. E equals m times a squared. That's not right. E equals m times b squared. Well, that's obviously not right. Then he put a c squared. It's just a joke. But how did he figure that out? I will never understand how this man came to understand the relationship between mass and energy. So I looked it up. Our bodies have, I forget the actual number, and I don't think I can find it in my notes, but we have the equivalent of a hydrogen bomb. If the energy, if the mass in our bodies was transformed into energy by this formula, it would blow up like a hydrogen bomb. How strange is that? Fortunately, it's fairly stable. Photosynthesis is a big deal. I actually, for some reason, get excited every time I think about photosynthesis. It just seems so remarkable that this star 93 million miles away is able to power this process of breaking hydrogen, splitting water apart, breaking the hydrogen off the oxygen, attaching the hydrogen to carbon dioxide. You end up with sugar, which is strange in its own right. So what's the deal with sugar? The deal with sugar is it has energy in it. That's why you can't feed it to kids. They start bouncing off the walls. Where's the energy come from? It's the energy of the sun that's bound up in the hydrocarbon bond. And if you break that hydrocarbon bond, that energy is released. That's the story with wood. I have wood burning in my fire. Those are hydrocarbons and combining with oxygen. If I blow on it, it gets hotter, more oxygen, hydrocarbon. Coal, it's hydrocarbon. Petroleum, natural gas, those are all hydrocarbons. They all are fossil sunlight. What's the name of that book? There's a book that has the fossil energy of the world. We're running on fossilized solar energy. It is finite, by the way. That would be a different story. Fossil fuels are finite. We can't live on them forever. So the oxygen is released into the atmosphere. Oxygen is a very reactive element. There would be no oxygen in the atmosphere if it wasn't constantly pumped there by plants. 21 the atmosphere is 21% oxygen because it is constantly pumped there by plants and other photosynthetic organisms. This is a statement by Lynn Margulis, very famous, now passed away biologist. It's photosynthesis is the most important single metabolic innovation in the history of life on the planet. The most important. Why? Because it creates all the food. This is the biomass of life on the planet. Most of the biomass on the planet is photosynthetic organisms. I'm not quite sure how accurate this chart is, even though this is out of a science journal. But there are other photosynthetic organisms besides plants, like diatoms, which I'm going to mention here. And they weigh a lot. So, and they are protists down there, that little dab given down there. I'm not sure this is 100% accurate, but it is out of a scientific journal. And it's good enough for us at the moment. It shows the power of photosynthesis. Photosynthesis makes most of the biomass on the planet. That's why it's so important. And I think I mentioned this last week. I can't get over it. You can Google photosynthesis at MIT, and you get this short 5-minute program of these graduates at MIT and these scientists from Harvard are interviewing them about what they know about photosynthesis. They hand him that piece of wood. He's got a seed in his other hand, and he says, "Where does that wood come from?" And they all say dirt, that the plants are sucking up dirt. So wrong answer. They don't know the first thing about the most important metabolic force on the planet. And they just got their degree from MIT. I just never can get over it. So what are plants made out of? They're made out of carbon dioxide. I regret to report, because people don't like carbon dioxide. They're 90% carbon dioxide. It's a magic trick. So this is another emergent property of the universe, because it's not just life. Life is emergent, but the universe is emergent too. There were many things emerged before life emerged on the planet. In the early universe, there were no stars, there were no planets. They formed. Fortunately, we don't have to explain how. But another emergent property is increased density of energy passing through structures in the universe. And so there's going to be a couple other images that make this a little more clear, but this is energy density per second, and it's in that little horizontal thing. It says erg, ERG, per second per gram. An erg is a very small measurement of energy. I one time saw it described as the amount of if a mosquito flew into a wall, it would expend 1 erg. Probably not accurate, but it's just a sense. It's not very much energy, but the numbers get big. The number of ergs get very big. It's just a way to assess energy density. So surprisingly, the sun is not as energy dense as the earth. Like I said, if our bodies were to expend the energy embodied in our mass, we'd blow up like a hydrogen bomb. So living things are more energy dense than the physical structures of the universe. And that's what that shows. And this may show it slightly more clearly. Graph. So galaxies are not energy dense. Galaxies, like Bill Bryson says in A Short History of Nearly Everything, space is extremely well named. Mostly there's nothing out there. Even though there are all these galaxies, there's so much space between them that even though they have 100 billion stars, the energy density is nil. The energy density is nil. Stars, there's a lot of energy, but they're so massive that the energy density is low. Assuming this is accurate, and this is from a guy at Cornell, a PhD physicist at Cornell, I forget his name. The point is that living things concentrate energy. So you have plants, not much energy, animals, brains. The human, 20% of the energy burned by the human body is burned by the brain. It's an energy dense structure. And then what? And then modern society. Why is modern society so high? Do we know the answer? The answer is fossil fuels. We have access to energy that is not, it's fossil energy. It's energy that was stored 50 million years ago. The thing won't move. There, it moved. So this is a graph of energy use by Homo sapiens over time. The bottom one there, which is slightly cropped, is 2,000 kilocalories per day. That's the human body. That's a consumption. That's how much energy, roughly speaking, the human body consumes. Hunter-gatherers, that number went up to 5,000 kilocalories per day. How did they do that? They learned how to harness fire to heat themselves, that's energy use, and cook food. Early agriculture. So the point is, even at the evolutionary trend of the universe is towards increased energy density. That is true for Homo sapiens as well. So here we're going after energy. Animals are eating the sun. Any living organism has the energy of the sun trapped in the hydrocarbon bonds in its body. This is a golden eagle. I just got this off the web. I don't know how anybody got this picture. It's a beautiful, beautiful picture. That eagle looks like it's dancing on that deer, but it's grabbing it and probably going to kill it. Why? Because it's going to eat it and acquire the energy that the deer got from eating plants, the energy of the sun from photosynthesis. This is a picture I actually took. That's why it's so bad, but I have more to say about it. It's not just bad, it's also interesting. I took this from the top of Eagle Rocks, which is part of the Pipestone Formation. I can see Eagle Rocks out my window. This is a picture of two juvenile golden eagles in a nest with, this is 100 feet up in a Douglas fir tree, and there is a dead fawn up in that fir tree. I got a call actually from picture. I told them about this nest and they went up to look at it. And I got a call. I said, "You got to come up here. There's now a fawn in that nest." Well, the adult eagle was able to lift that fawn somehow high enough to get it into that tree and feed it to these. I think I circled the fawn. That's the fawn, part of the fawn. You can see the spots on this fawn. There was another interesting aspect of this nest. One eagle was feeding on the dead fawn, and the other eagle was perched on the edge of the nest. You can somewhat see it over on the right there. The one eaglet would not let the other eagle eat, and I actually went up there the next week, and the second eagle was dead. You know, their eggs are laid asynchronously. They're not laid in the same day. They're laid a few days apart. So there's one eagle that's always 3 days younger than the other eagle. It's less mature. It's less big. It's less aggressive. If there's not enough food, starves to death. In fact, the other eagle might kill it or push it out of the nest. It's a rough world. It's a good book, Eating the Sun, very good book, about what we have been talking about, capturing the energy of the sun in photosynthesis and in hydrocarbon bonds. I got these pictures off the web. That is a cougar stalking a bighorn sheep. And here it is killing the bighorn sheep. It's just the way the world works. It's very hard to get used to, but that's the way it goes. There is no guilt. It's just a beautiful picture of a cougar. There is this beauty. I mentioned that in the first slide. There's this combination of what to call it, the painful aspect of the planet, that everything eats everything else, and then the beauty of almost every organism. This is a cartoon my father sent me many years ago. There's a lion judge and a lion defendant, and the lion defendant apparently killed something, and the judge says, "You were hungry, case dismissed." That's the nature of life on the planet. That's why there's a lot of bad news, but there's also a lot of good news. And the good news is that life is self-regenerating, and the planet itself is, I would say, self-regenerating. It acts like a living organism. We saw that with the recycling. Who would think that the continents would be worn away by erosion, worn into the ocean, and then drawn down by subduction back into the mantle and reappear as magma? Well, that's what happens. But all the elements on the planet are cycled. So this is a kind of, I think, a charming little image. And I realized I don't know if I can remember what's what here. We should be able to figure it out. So, uh, it's carbon cycling. Ah, I think, see, the empty circle at the top goes into the tree and turns into something green. That's photosynthesis. The carbon is captured. Carbon is captured by photosynthesis. It goes down into the soil. If the plant dies, it's released by combining with oxygen, and the energy that was captured is released. So it's just the cycling of energy and elements on the planet. You know, the unfortunate thing is humans, all the other animals are integrated into this process, and humans, because of the incipient intelligence, have separated ourselves apart. But it is something we're capable of learning, that everything cycles. We can't throw things away. This is the same theme, that these different aspects of the planet, the geosphere, says lithosphere here, the hydrosphere, water, biosphere, they're interconnected. They affect one another. The atmosphere is 79% nitrogen. It's put there by bacteria in the soil that break living organisms apart and release the atmosphere, release that nitrogen. It's 21% oxygen, all put there by photosynthesis. So the atmosphere is created by the biosphere. The hydrosphere is greatly affected by the biosphere, and of course, the biosphere is dependent upon it, and the lithosphere supplies the elements for life. It's a big story. It's a big story, but it's been a journey figuring it out. So this is a picture of Humuncules. This is what Nicholas Hartzucker saw in, I'm not sure, about 1600, the first microscopes. He looked at sperm, and he saw small humans encased in the sperm. Now, apparently, he didn't quite say that. He just suggested that he thought they were small humans. And so then these are those small humans that are in the sperm lined up on a pinhead. And this is how the point is, everything we know we've had to figure out. It all starts with misconceptions. It all starts with misinterpretation. It all starts with superstition. And there is still so much superstition on the planet. It blows my mind. So this is Anton Leeuwenhoek, also soon after, very similar time period, because they were just starting to develop the most primitive microscopes. And Leeuwenhoek, this is about, I think, 1700. He saw the water was full of living organisms. He called them animalcules, and people wouldn't believe him. He was derided by society that there could be these organisms. They could not believe that there was more to life than their belief systems. So science is a powerful force. Science doesn't explain everything. The best thing about science is, in a sense, arguably, it dispels our myths. It dispels our myths. This was a myth. I think I showed this last week, or the first week, but it's, to me, it's so powerful. Human beings, we're just inherently self-centered. We can't help it. The only counterweight is intelligence. Intelligence is an emergent force of the universe, and it is emerging. It's discouraging at times. So what? So we thought,
checking all those points. Library.
Is at the center. The sun just came up over there on the left, and it's going to go across the sky, and it's going to go down on the right. We must be at the center. Well, it took the first people to suggest, and I think I mentioned this before, but Giordano Bruno, he was burned at the stake. He was burned at the stake. People hate the truth. They just hate it. Part of the problem is it takes us out of the center, and we want to be in the center. It's not the best thing for us to be in the center, but we still have this attraction. Galileo was sentenced to house arrest. Yeah, that was soon after Giordano Bruno. At least they didn't kill him for saying it was heliocentric, that it was sun-centered. It was more of a blow when we figured out that those dots in the skies are other stars. They aren't just holes in a drapery. We aren't the center of the universe. So it's been a journey, and we're still on that journey of waking up to our planet. These are some evolutionary organisms, because we're trying to get the life on the planet. These are single-celled organisms, from the above left: red algae, green algae, ciliag, golden algae, what's that, radiolarian, So on the lower left is Giardia. We've all heard of Giardia. It's a single cell protist organism that infects our gut and makes us sick. Amoeba, slime molds. Life started out as single cells. Life started out as prokaryotic cells. Endosymbiosis created eukaryotic cells, and life has diversified ever since. Life had to colonize. Life evolved in water. It had to emerge from the water one way or another. We talked about that a bit with plants, how plants managed to do that. Animals had to manage to do it. There are numerous organisms that have lives in both environments. So dragonflies are larval. There's a lot of aquatic insects. Upper left is a dragonfly. It lives its early life as a larva in the water. It crawls out onto a stem, cracks out, metamorphoses into a winged insect by magic, and flies away. And then mayflies live their larval life. That's a mayfly larva in the center picture lives most of its life as an aquatic insect in the water. It has those gills on its abdomen to acquire oxygen from the water, and then metamorphoses into a winged creature that is all eyes. That thing that looks like a hat is its eye, and has no mouth. It's in this order called Ephemoptera, ephemeral creatures. It never eats. It only lives about 5 days. As an adult, what's the use of that? It's an organism that lives in the rivers. It's constantly being washed downstream, and so it needs a way to get back upstream. That larva cannot swim upstream, so they hatch out as winged adults. We have these clouds of mayflies that emerge all at once from the water. They mate. They have reproductive structures, but they have no mouth. They mate, they lay eggs, and they have you thank the diatom today. I put that in there because apparently, so diatoms are photosynthetic organisms with shells made out of silica, which is glass. Their shells are made out of glass. Diatom means something like two sides. Diatoms come apart. You could take that star in the center apart. There's two sides, they fit together. Same with the other ones. The picture at the bottom is a diatom bloom off the coast of Alaska in the Bering Sea. Diatoms Diatoms produce at least 20% of the oxygen. They're photosynthetic of the oxygen in the atmosphere. Diatoms, which we barely know exist, are major players in the force of life on the planet. And so they're photosynthetic, so they're creating food. There's a story that I put in The Naturalist. That obviously I found it somewhere else. Grasses are flowering plants that live on land, obviously. They're recently emerged, like 50 million years. Grasses, flowering plants are 130 million years. Grasses are flowering plants, but they're wind pollinated, so they aren't showy. They are beautiful. They take silica up into their physical structure to prevent herbivores from eating them. It doesn't work, but it worked at first. So they turn silica into an organic structure that when the plant dies, washes into the stream and down into the ocean. Grasses increase the amount of silica dissolved in the water in the ocean greatly, and that's what has created this huge bloom of diatoms in the ocean. Diatoms have increased enormously in number in the last 30 million years, and they're major players on the planet. They produce at least 20%. I have in my notes, it said, which I wrote down from Google, so it must be true, it says 20 to 50%. So I'm going with a lower number. I don't know why that came up. Maybe they're out of order. I don't know what's going on. So I put this in. These are bumblebees in the Methow. And the point is this diversity that we have in the Methow that we would not imagine, except there are people who apply themselves to any particular aspect of life here in the Methow, in our area and on the planet. People become biophiliacs. Biophilia means love of life. I think E.O. Wilson coined that term. So John Colt, who lives in Carlton, is our most knowledgeable. He didn't put this together. This is from the Methow Naturalist, but he's put something probably better together. John Colts lives in Carleton, and he has a love for bumblebees and spends days and days traveling around the watershed studying the diversity of bumblebees and identifying the species that we have. And he has good material on identifying them if you find yourself drawn to. So life is continuing to evolve. There were no vertebrates. Life emerged onto land. There were no vertebrates. Some of the first vertebrates on the planet were lamprey eel. And they are so ancient, I forget how ancient, but there are fossil lamprey eels that go back millions of years. It might be 300 million. I can't remember. They seem like devilish and imbecile, but they're a valuable part of the ecosystem. They were numerous in the Methow River, and now they're almost extirpated. They're almost gone. You can count on two hands the number of. They are migratory. The adults migrate down the Columbia to the ocean, live for some number of years, 2 or 3 probably, and then come back up the Columbia to the Methow to spawn, lay their eggs. I've never seen the eggs, but I have seen the young in the Methow River. The young are filter feeders and filter organic matter out of the river and purify the river. They have their place in the ecosystem, but they're almost gone. They are scary. So these are organisms. We're going into some of the organisms of the Methow. This is a tailed frog. It's fairly unusual in the Methow. It lives in our mountain streams. If you hike up Cutthroat Creek Trail, you go past the lake and you go another 200 yards and you start crossing a couple of streams coming down out of the mountains. Those streams have tailed frogs in them. They live as tadpoles in fast, clear mountain streams. The tadpoles have suckers on their mouth and they hold onto the rocks with a sucker. You have to turn the rocks over. I think I forget the name of the creek. If you go from Rainy Pass and hike up towards Cutthroat Pass, that creek is full. You go a mile and cross a creek. That creek is full of tailed frog larvae. So an interesting aspect of tailed frogs is their 3 closest relatives are in New Zealand. So either that frog hopped across the Pacific Ocean or the continents have moved over time. And of course, the truth of the matter is the continents were once all joined together, and that's probably how these dispersed across the continents long ago. So this creature's around, hard to find. Mountain beaver. Mountain beaver are considered the most primitive mammal on the planet. Evolutionarily, the most primitive planet on the planet. It has to do with the bone and muscle structure of its mouth. A little hard for me to understand. I was reading about it this morning, but they are primitive, and we have them here in the Methow. So we have the evolutionary story of life on the planet embedded in the Methow Valley. These are not as rare as they seem. Somebody saw one running across a road near Peregrine Creek, which means they're down fairly low. When you're hiking up our mountain trails and you cross a wet place in the forest, there's often a hole in the ground next to that wet stream. It could be not much of a stream, just a wet place. Those are mountain beaver holes. They're not uncommon. I saw one once coming down Buttermilk from Hoodoo. Somebody said, "What's that?" And I turned around, and a mountain beaver, I saw it for 2 seconds. It ran between two of us hikers and then disappeared. They're nocturnal and secretive. You don't see them very often. We may need to speed up. 29. This is a human egg. It's a single cell, a combination of sperm and egg. It's been fertilized or it hasn't been fertilized. I'm not sure which, but even if it's fertilized, it still becomes a single cell. The interesting thing is we start out as a single cell. Humans start out as a single cell. And how is it possible that all of the information necessary to make a human is embodied in that cell, and in the evolutionary process of the embryo recapitulates the evolutionary journey, at least of vertebrates? What do I mean by that? This is a young, I don't forget, the next picture shows how old this thing is. a couple of weeks, a week or two, as the egg starts to develop, it has gill slits. Why does it have why is it, it has a tail, which are later reabsorbed by the developing embryo. Why? Because life re-travels the evolutionary journey of all organisms. We start out as a single cell. So this is a cute little graphic of embrace your inner fish, because we are related to fish. So this is where that graphic came from. I think this might be, I forget who did this, maybe Haldane, that the guy I've mentioned. I think I have a red line here to show these things are labeled down at the bottom. This is evolutionary journey of a fish. First week, here's a 1. Second week, third week. The point is they all look the same. At the first week, the embryos all look the same. They all have gill slits. They all have tails. It might be slightly exaggerated in humans here, but it shows the evolutionary relationship of at least all vertebrate organisms. We need to speed up a little bit. So fish, that's a Chinook salmon in the Methow River near the Winthrop Post Office. They're a big story. I'm sure you all know the basic story of the salmon, but they're anadromous. Anadromous. They're born in freshwater streams. They swim as juveniles. They swim to the ocean. They live for 1 or 2 or 3 years in the ocean, depending on which species of salmon. They return 100 times bigger than the fish that swam to the ocean. What do they bring back? They bring back the nutrients that are rushing to the ocean, rushing downstream in all the streams. The fish bring those nutrients back and fertilize the uplands. They used to be, I think, 6 million salmon used to migrate up the Columbia, and maybe 100,000 into the Methow. And they've been greatly diminished, as we all know. Just that we have a lot. This is just a lot of salmonids in the Methow. Interestingly enough, half of them are non-native. We don't have time to look at that. So life emerges onto land. How does it do it? Well, these mud skippers are a good example. They live half their life in the water and half their life on land. They come out of the water. It's one thing, it's safer. There are fewer predators, and they breed on land and then return to the water. So they're an interesting kind of picture of how life could have emerged. Amphibians, I mentioned, the word means 2 lives. They start out in the water and then they come out onto the land. So the eggs are almost always laid in water with amphibians or in wet places. These are numerous egg masses that one frog has just below it. You can make out a circle of eggs. So the male and the female lay about 500 eggs. How many of those eggs have to survive to replace the parents? Obviously, the answer is 2. So out of that 500, on average, 498 of them have to not survive to reproduce, or the world would fill up with frogs. There are a lot of frogs, but it hasn't filled up with frogs. This is an interesting evolution story of how life adapts to changing circumstances. There are these English peppered moths. It's a story from England. The English pepper moth. There is a white moth in this upper picture that is impossible to see because it's camouflaged. It has the same color as the birch bark that it's landed on. I can barely make it out. I think that's the body of the moth and the wings are here. It's camouflaged. If a predator comes to eat these moths, the one that is dark and is not camouflaged is the one that's going to get eaten. The trees in England during the Industrial Revolution, they were putting so much soot into the air that everything was blackened. This is a typical birch tree after it's got soot all over it. And now the white moth stands out. And there actually was a measured shift from dominant white moths to dominant dark moths in the 1800s, because this now became, by chance, by human impact on the environment, the camouflage moth, and the moths they were selected for dark moths instead of white. It just shows that natural selection is real. Evolutionary journey of Methow wildlife. This is what they're all doing. This is what that eagle was doing in the first slide, eating that deer, and the coyote wanted a bite of it. So, a brief review. How many amphibians do we have in the Methow? So I put this together. I think there's 7, but these things are hard to remember. It was a point. I thought, how come you can never remember this stuff? How come you can never remember this stuff? The reason is the information is infinite. That is the reason. Insights into the planet, knowledge about the planet, there's no end. There's just no end. And if you're not interacting with the information, you don't incorporate it. You can't remember it. So we have, I think that's it. I forget if yeah. So there's 7 species. They're all fascinating and beautiful. They all eat other living things. They're carnivores. Everything eats everything else. Here's a couple of our species. Don't see these guys too often, but they're around. They tend to live subterranean, underground. These are long-toed salamander eggs. They do have to come out from underground to lay their eggs. This is a scene I saw up near Black Pine Lake. There's a pond up there, Black Pine Pond. These are western toads in amplexus. The male releases, he's grasped the female when she's laying those eggs in double strands, and she doesn't know what she's doing. Sometimes she comes out of the water and lays them over the land. It's a pretty blind process. He's releasing sperm, they get fertilized. How many of them have to live to replace the adults? 2. So life needed to colonize land. Reptiles figured out, somehow evolved through natural selection to lay eggs that had a calcium shell and my phone's ringing. Sorry, I can't answer it. It doesn't last very long. Anyhow, it's about the colonization of land. These are rattlesnakes at Pipestone Canyon. We found this den. They den up in the fall and they're underground in the winter, and then they come out. I can't stop that phone. And we found this den. Well, we visited that den. I think I brought somebody to show it to them a week later, and somebody had killed half the rattlesnakes. And rattlesnakes are critical to the ecological health of ecosystems. They eat rodents. Which would you rather have, rodents in your grain or rattlesnakes in your yard? So we're just now looking, we're going to speed up a little bit, but looking at some of the organisms we don't see too often, but we have these painted turtles. That's why they're called painted turtles, because they're painted. I have a garter snake den on my property. This is right here near the house, and they're all down there under the rocks right now, and they come out every spring about April 1st, and they have to warm up, and they pile up on top of one another like that. Reptiles of the Methow. How many? I think there's a few more. So just that these organisms are all here. They all have lives. They've all evolved over time. They're all beautiful, and they're all meat eaters. They're all killing things to survive. This is a bird's foot, and the point is it looks like a reptile because it's scaled, and birds did evolve from reptiles. And now we have so this slide I put together some years ago. I don't know how many, maybe 8 years ago. It says 270 bird species, and I had to correct it because now we know of 282 bird species. We don't know for sure what's here with us. And the more we pay attention, the more we find. So there are a lot of birders in the valley, and they report birds, and some of us keep lists, and so these lists keep growing. We're just learning about what the organisms live on the planet. That great horned owl is in a tub that's up in a pine tree nested there here on my property. The bald eagle is stuck. The bald eagle has his foot caught in the crotch of a branch. I was walking on land near here, and I found it hanging there upside down. And the smoke jumpers, I reported it, and the smoke jumpers organized a rescue mission and cut that branch down. And the eagle flew off, but its foot looked like it was broken. One foot was hanging down. Anyhow, that's why in that strange position. These are golden eyes, 2 species of golden eyes. And the point of interest to me here is they obviously have a common ancestor. They obviously speciated, and they did it by partitioning the habitat. They arrive in the Methow on different dates. They stay in the Methow for different periods. I mean, it's not all about the Methow, but their lives here indicate their larger range, and they utilize different aquatic habitats. And over time, they they differentiated into two species. And that's why we now have 20 million species on the planet instead of just one. One of our great characters in the Methow, the harlequin duck, that somebody said it looks like it was assembled by a committee of first graders. They're only here in the spring. Well, the females stay and nest. The males are only here for about a month. They swim from the ocean and mate with the females and then go back to the ocean. We don't have that many duck-billed platypuses in here in the Methow. We don't have any duck-billed platypuses. I just put it in because it's sort of a bridge species. You know, it has characteristics of reptiles, birds, and mammals, and it's on the ancient continent. It's on the continent of only found on the continent of Australia, and it shows characteristics that it lays eggs. It's a mammal that lays eggs. How about that? The heart has evolved over time from a 3-chambered heart to a 4-chambered heart. Why? It more efficiently captures oxygen from the blood and circulates that oxygen around the body. What does the oxygen do? What does the oxygen do? The oxygen breaks up the hydrocarbons that we take in as food and increases the energy available. So mammals have 4-chambered hearts because we are so active. We don't hibernate during the winter. We need to go to Hanks and get food. Oxygen in the atmosphere has increased over time because of photosynthesis. It would last a couple of years. If photosynthesis stopped, all the oxygen would leave. It would react with other elements, create molecules, and precipitate out of the atmosphere. What's the oxygen used for? We just answered that question. It's used to break up the hydrocarbons, release the energy of the sun. Mammals have evolved over time. There were no mammals. Mammals, through natural selection, evolved various characteristics that allowed them to better utilize the energy captured by photosynthesis, including hair, which keeps heat in, burn less energy, allows them to stay active through the winter. Parental care, even blue whales nurse their offspring. By the way, the biggest creature that has ever lived on the planet, the blue whale. Characteristics that evolved over time, they're all actually increased energy density. That graph I showed earlier, life has this trajectory of increasing complexity and increasing energy density. This is the smallest creature in the Methow montane shrew. I looked it up. It's way under an ounce. It weighs way under an ounce. But you know, they don't hibernate. They're active under the soil in the winter. Amazingly enough, I think this is the largest creature in the Methow. Moose, I forget, I think up to 3,000 pounds. I looked up grizzly bear. We don't have any grizzly bears at this time, but they were nowhere near. I was surprised. They only go up to about 600 pounds. This is at Roger Lake, which is, you know, the base of Tiffany Mountain. Our carnivores, these are our ferocious carnivores. Bunch of coyotes. I was with Annika. They heard us approaching. The parents ran off. We saw the mother run up the hill, and they all came out of their den, and they ran down the hill to our feet, and then they got scared and ran back. It was a great experience. These are red squirrels. Scott Fitkin found 2 baby squirrels taken out of their nest and gave them to me, and I took them to camp, and they became the camp mascots. The camp kids fed them with eyedropper milk through an eyedropper. So mammals. So the question is, who lives here with us? Who has the gift of life and the complexity of life? How many? Well, we don't know for sure, but we do the numbers, and I'm going to bring them up. But could we guess? No. I put these numbers in here, and I can't remember. How many bats are in the Methow Valley? I don't know. Kent Woodruff knows because he studied bats. Rabbits, pikas, 1 pika, 2 species of rabbits. I think that's up to date. Rodents. How many apes? 1 big ape. 18 carnivores, 6. So we are at the end. But this is a great story, and you know the basics, but this is like 15,000 years ago. These are Pleistocene megafauna that were here in North America, not necessarily in Washington nor in the Methow, but some of these were in the Methow. Undoubtedly, because the Methow was completely formed 15,000 years ago. The ice was starting to melt. Some of these fossils have been found certainly in Washington, but they're megafauna. The whole landscape was completely different just 15,000 years ago. These all went extinct. By 12,000 years ago, they were all gone. We had llamas. We had 3 species of elephants in North America. We had I forget the ground sloths. Ground sloths. Why did they go extinct? It's not well known. It's not fully known, but these are spear points that were found in East Wenatchee, a cache, a collection of spear points. I forget how many, like 25 in a cache in the ground in an orchard in East Wenatchee. I think in maybe 1987. Look at the size of those. What do you need a spear point that size for? The only the only thing you can kill with a spear point that big is probably a mastodon or a mammoth. They're just gargantuan spear points. So this is these are mammal extinctions over time. This is taken out of E.O. Wilson's book, The Diversity of Life. But in Africa, where humans co-evolved with animals, the top picture there's not been the kind of animal extinctions that the other continents have experienced that were colonized by humans in more recent time over the last I forget for sure when they first arrived. Does it say there? Yeah, it does say Australia 10,000 years ago. The animals had not co-evolved with humans. All of the large species were doomed to extinction after humans arrived. So that's a piece of evidence that it's human caused. I showed that picture of the little lion that was being judged. It's not a matter of guilt. It's a matter of intelligence, really, to take care. We are commissioned to be stewards of the biosphere, and we're growing in that direction. We need to speed up a little bit. So this is that same cartoon, but I had cut off the last character, which is Homo sapien, which stood up, became bipedal, and it's accurate that we wonder what it's all about. Well, it may be about increasing intelligence and stewardship of the biosphere. This is the last slide. Evolution. We have granite over there on the left. The continents have grown over time. Life appeared and has diversified, and then the animals appeared and humanity appeared. And I love the quote: time is a river passing events and strong as its current. It's just that everything changes over time, and we are in the river of time, and we're fortunate to be here. How'd I do? Oh my God, I went over time. Well, that's the end of the story. Tracy, do you still exist?
I am here. Can you hear me?
Yeah.
That was great. Thank you. Yes, we've got some clapping. Any,
Well, thank you.
yes,
Oh,
we're
Asya.
a
So
little over. If
let me
anyone
point
needs to
out
go,
here,
go ahead. But if
Tracy,
anybody has a question, yeah.
let me point something out. I can see in my list of people, which I can only see 5 people. I don't know what you can see, but Asya is online. I don't know if she's there. Asya lives in Moscow. Asya and Julia live in Moscow. And I sent them the link like last night or this morning. So Julia and Asya, they live in Moscow. They're very Russian. They're Russian people. They've been to the Methow 2 or 3 times. I forget how many times. And Masha, you can unmute yourself if you want. I don't know if you can hear me, and what is that darling little creature? I forget what those things are called. Anyhow, it really, to me, yeah, Asha unmuted herself. You can put your camera on, Asha. We want to see you. Anyhow, Asha, what do you have?
Yeah, Dana, if you
Julia.
want to quit sharing, then we'll be able to see people
How do I do
better.
that?
It's
Stop share.
there's a little stop share, yeah. There we
Stop
go.
share. So people, obviously, you can leave anytime you want, but we might be able to get a word out of Asya. There's Asya. I can see her. Is that you, Asya?
Hi there.
And
Yes.
Julia. So they're in Moscow. This is the magic of modern technology. it's nighttime. They don't have any lights in Moscow. That's why it's so dark. No, I'm just teasing you. But it's just so exciting. So both of those people, Asya, who's the daughter of Julia, has gone to river camp. How many times, Asya? Twice?
Yes, twice.
Twice. Listen to that nice accent. Talk to us, Asya.
Awesome.
We want to hear your Russian accent. Anyhow, it's just so touching to see you. And you think of the conflict. There is a danger of nuclear war between Russia and the United States. And look at how charming these human beings are. Here's our enemies, Julia and Asya. It's insane. People are crazy. We need to get over it. We need to get over ourselves.
Thank you very much for the lecture, Dana. It was, as always, interesting, and I recognized some of the pictures from the kids' camp.
Yes, thank you very much. I also enjoyed it.
I'm so glad. Thank you so much for tuning in. I can't believe you can make it all the way from Moscow to here, but it's great to see you. Okay. So I guess we, what's that word? Digress.
All right.
Anyhow,
Yeah, thanks so much.
Thank you, people, for hanging in there.
Absolutely. Yeah. I'm going to stop the recording. Thanks so much, Dana. That was fantastic once again.